Welcome to the second video for the angular kinematics stuff. So in this second lecture video, we'll talk about angular displacement and distance, angular velocity and speed, and angular acceleration. And as you know, these are all different ways that we can describe angular motion in the same way that we were able to describe linear motion. Angular displacement is defined as a change in angular position of a rotating object. And this formula is the same as it was for linear displacement, where your displacement is equal to your final position minus your initial position. But now the final and initial positions are angles. An angular displacement is a vector quantity. So remember that this means that angular displacement is defined using a magnitude and a direction. And so using the right-hand rule, you can establish that the direction can be either clockwise, which would be negative, or counterclockwise, which would be positive. And the units for angular displacement can be degrees, radians, or revolutions, which we should all be familiar with by now, thanks to the first lecture video. So let's do a little virtual exercise here to make sure that we remember how to use the right-hand rule. Apply that right-hand rule to your left elbow joint as you flex and extend your left arm. So if you establish the direction of the axis of rotation as positive towards the right side of your body, so your thumb should be pointing towards the right, is flexion positive or negative? What do you think? So your fingers should be curling towards you, towards your shoulder, which would make flexion positive. Okay, let's try an angular displacement calculation now. So here we have a baseball player that's being evaluated for their shoulder joint range of motion. And the measurement begins with the player's arm at their side, as you can see in this picture on the left. So this initial angular position is 5 degrees from this vertical plane here. So the player then raises their arm away from their side as far as they can by abducting their shoulder, which gives us a final position of 170 degrees from the vertical plane. And what is the angular displacement of the arm? I invite you to pause the video here and do the calculation yourself. So we're looking for the angular displacement of the shoulder here, or of the arm, when we go from this position to this position. Okay, so first, the axis of rotation is this anterior-posterior axis, so coming right out from the shoulder. And we know that the plane of motion is the frontal plane, right? So this sort of plane here is the frontal plane. And we know that the equation for angular displacement is the final position minus the initial position. So that's 170 degrees minus 5 degrees, which gives us 165 degrees. Now that's the magnitude of the displacement, but remember that angular displacement is a vector quantity, so we also need to assign the appropriate direction here. And using the right-hand rule, if you point your thumb in the positive direction of the axis of rotation at the shoulder, so in this case, your thumb should be pointing towards you if you stick your hand right on that shoulder joint there, then you should establish that your fingers are curling in the counterclockwise direction, which means that this displacement going from 5 degrees to 170 degrees is in the clockwise direction. So the angular displacement is negative. So it's negative 165 degrees or 165 degrees in the clockwise direction. Now that we've seen angular displacement, let's compare it with angular distance. So the angular distance is the sum of all angular changes that have been undergone by a rotating object. It's denoted by the Greek letter phi. And the important distinction between distance and displacement, as you know, is that distance is a scalar quantity. So it's independent of direction. It's only defined using a magnitude. And it has the same units as displacement, so degrees, radians, and revolutions. Let's compare angular distance and displacement visually. So let's say we have a marble that's attached by a string. So there's the string, and then this is the marble over here. So the picture on the left here shows the marble starting in its initial position on the left, and then it swings to the right, and it ends up in this final position here. And recall that the angular displacement is the difference between final position and initial position. So it's only concerned with the marble's motion from this initial position and this final position, whereas the distance is the sum of all changes. So it includes this middle part here, if that's what you want to call it, where the marble went all the way to the right first before stopping in this final position. Okay, so that's what these black curves are showing you here. Displacement is only concerned about these two positions, whereas distance is the entire motion. So going from the far left to the far right and then ending in the middle. Angular velocity is defined as the rate of change in angular displacement. So in other words, it's a change in angular position, so delta theta, over a change in time, delta t. And angular velocity is abbreviated with the Greek letter omega. Angular velocity is a vector quantity, just like linear velocity, so it has a direction also associated with it. And the direction of an angular velocity is also determined using the right-hand rule, same as angular displacement. Its units of measurements are radians per second, degrees per second, revolutions per minute, anything that's a change in angular displacement over time. Now, angular speed is defined as the rate of change in angular distance, and it's abbreviated with the Greek letter sigma. Angular speed is a scalar quantity, so it only has a magnitude, and its units of measurement are radians per second, degrees per second, revolutions per minute, anything that's angular distance over time, same as angular displacement. Okay, so let's try a calculation now to put this to practice. Adelaide performs a figure skating jump where she rotates around her longitudinal axis 3 times while she's in the air. The time it takes to complete the jump is 0.8 seconds. What is Adelaide's average angular speed during this jump? Provide your answer in degrees per second. So I encourage you to pause the video here and try this calculation on your own. Okay, first, what do we know? Well, she does a spin in the air that's 3 turns or 3 revolutions. Next, we need to, we also know that the time is 0.8 seconds. So next, we need to convert our revolutions to degrees because the question asks us to provide our answer in degrees per second. So we know that in one revolution, there are 360 degrees. So in 3 revolutions, there are 180 degrees. So if we put all of this together in our speed equation, this is what we end up with. So we have a distance of 1,080 degrees, not 100, 1,080 degrees over a time of 0.8 seconds, which gives us an angular speed during Adelaide's jump of 1,350 degrees per second. That's pretty fast. Okay, the last topic to discuss in this lecture video is angular acceleration. Angular acceleration is the rate of change of angular velocity. So in other words, as the equation states here, angular acceleration is a change in angular velocity, so delta omega, over a change in time, delta t. angular acceleration is abbreviated with the Greek letter alpha. And just like displacement and velocity, angular acceleration is a vector quantity. So it has a magnitude and a direction. And the right-hand rule is used to describe the direction of angular accelerations. Its units of measurement are radians per second, or radians per second squared, degrees per second, degrees per second squared, or any kind of unit of angular velocity per unit of time. And angular acceleration occurs when something is spinning faster and faster, or slower, or when the spinning object's axis of spin just changes direction. Okay, so another practice calculation here. When Josh begins his discus throwing motion, he spins with an angular velocity of 5 radians per second. Just before he releases the discus, his angular velocity is now 25 radians per second. If the time from the beginning of the throw to just before the release is 1 second, what is Josh's average acceleration? Angular acceleration, I should specify. Again, I encourage you to pause the video here and try this calculation on your own. So first, what do we know? His initial angular velocity is 5 radians per second, and his final angular velocity is 25 radians per second, and the time is 1 second. And we, of course, know our equation for angular acceleration. So let's substitute everything into the equation. So we have our final angular velocity minus our initial angular velocity divided by time, which gives us an average angular acceleration of 20 radians per second, or 20 radians per second squared in the same direction as Josh's spin. Now, if the final velocity would have been smaller than the initial velocity, then we would have obtained a negative acceleration, which would mean that the acceleration would have been in the opposite direction of Josh's spin because he was slowing down. Excellent. So in this lecture video, we learned about angular displacement and distance, angular velocity and speed, and angular acceleration. And these are all different ways that we can describe angular motion. Now, in the next video, we're going to combine what we now know about both linear and angular motions.